Hello everyone, my name is Michel Schildmeijer and I'm from Amsterdam, the Netherlands. I'm happy to attend the Cloud Native Data Management Day, and I will present for you how to hypervise your containers and how it will protect your data. So I hope you enjoy my session, and well, if you have questions, let me know. Since the rise of cloud, DevOps, microservices, plus a lot of other new technology trends, also, infrastructure has made a major transition into how to build, provision, and operate a live production, serving all the needs you have for a 24/7 high demands of new, better functionality and higher demands in non-functional requirements such as performance and scalability. And transitioning such an existing infrastructure into a container-based landscape is something which has to evolve within an organization. It will be not an easy task. There will be a lot of resistance against new ways of working and new technologies because the production situation has to continue and has to be stable and everything. And one of the key areas within production live situations is security. If you look at the top trends in container native landscape, then you can see the prediction of Gartner in 2019, already 2 years ago, before the entire COVID crisis. At that time it was less than 30% of the organizations run some form of an application container in production. And right now you can see an increase which will end up in more than 75% in 2022, which will be the prediction of Gartner in this case. And if you look at the top 6 key areas of container native landscape, then everything around DevOps comes along, like lifecycle management, orchestration, monitoring and automation. But the number one in this is security and governance. And these 6 elements, when using application containers in production, still the security and governance has been listed as the number one priority. So every company which is starting to do this should take that into consideration and make a good plan of how you will protect your infrastructure, your data, and everything which is coming with your containerized application. Container technologies, of course, in the buzzword area. All the technology around it is kind of a buzzword, but let's investigate what do we mean with container technology. What is a container in fact, and what's the difference between a virtual machine and a container? So I guess bare metal server, that's easy. You have one server dedicated with one operating system and no splitting up. It's just one big server running some storage, some applications, maybe some databases, but all on one operating system and using all, not sharing any resources, having their dedicated process, their own piece of memory, and nothing more. So when you look at virtual machines, before the containers gain more and more popularity, the prior approach to get more out of your server is to virtualize. With virtualization, you can have one physical or maybe multiple physical servers in your data center and share resources, share like CPU, like memory, along these virtual machines. But these virtual machines themselves are isolated and don't know anything about what's underneath. They don't know anything about the other virtual machines which are running. So in contrast with container technology, the server runs multiple operating systems on the server, and all these virtual machines have some kind of a emulation layer, virtualization layer, using a hypervisor. And when you look at containers, containers are in fact small units, configurable units for a small subset or a small part of an application or an application. It also matches the microservices strategy where you try to break up your large application into pieces, and you can containerize them to have more broken parts of your application. And when you look at containers, they can share the operating system kernel. There's no hypervisor, but you have some kind of a layer in between, software layer, which makes it able to run the containers as a process. It runs as a process, and you can run with some software in between and have some networking, have some storage, so you can isolate them with your software. The most well-known software is of course Docker software. So Docker is not a container. Docker is the software which makes it able to run a container. When you have a container, the static part of it, the runtime is the process, the static part is the image. All your application and infrastructure bits are packaged in an image, and it can be placeholders. So if you run a container, you start it up, then you can have some kind of a property which tells the container where to run, with which storage, which network, all those kinds of things. Now the concept of containers is not new. With the first commercial version of Unix, which came out in 1997, the concept was already there, which was called chroot, and chroot is the concept of an operating system call to change the root directory of a process and its children to a new location on your file system, and this is only visible for this particular process. So the idea of this feature is to provide an isolated part of the disk for every process which you attach to it. And later on it was added to FreeBSD as well, which was called FreeBSD jails, and it's one of the earlier container technologies introduced beginning of 2000, and it's actually a bit similar to root, but it includes some extra features for isolating file systems, users, networking, etc. So as a result, you could provide means of assigning an IP address for each jail or container, custom software installations and configurations. Another container technology is process containers, which you might now know as C groups, container groups, but the first implementation of this was in 2006 by Google, also for limiting, counting, isolating resources, like CPU, memory, disk I/O, network, to a collection of processes, and later on it was renamed to C groups or control groups. And merged in that current year Linux kernel. And some other technologies like Linux containers or LXC was the first complete implementation of container manager on Linux platform, and it was delivered in some libraries, liblxc libraries, and it provided language bindings for a certain set of APIs in Python, Go, Ruby, Haskell, and contrast to other technologies. In contrast to other technologies, it works on a vanilla Linux kernel without any patches, so you can use it out of the box, in fact. And besides that, there are a lot of others. Container technologies available. but these are the most important ones. Looking at this diagram, you can see the differences between what's a virtual machine and what is a container. And you can see when you look at your virtual machine, then you have your operating system and your server, your core server and your core operating system. And on top of that, you have a hypervisor, an engine, a virtual machine engine to host all the virtual machines on your server. And the server you can share memory, CPU, storage, but in an isolated way. So you can give dedicated resources to a virtual machine. And you have also configuration where you can share or do some flexible work in assigning CPU and memory. And on top of that, you have your guest operating system of your virtual machine and installed your application, binaries, libraries, databases, everything on your virtual machine. And within that virtual machine, on that guest operating system, it doesn't know anything about the outside world. And when you look at container technology, a lot of things are similar. So you still have your server, your core operating system, but then you get something else. You get the containers engine, the software which can run containers and have communication outside of the container, have networking, have storage, everything. And within the container, you have your application binaries and libraries, just a small set of binaries and libraries only necessary to run your application. So no extra overhead of extra software. It's also a philosophy to keep your container as lightweight as possible. Looking at the security aspect of your containers, you have to identify the critical points where you might have security issues. And I've drawn up some schema flow of how a container is built, pushed, deployed, how this flow will go in a production situation. If you look at from the left to the right, then in first you see your developers are developing application code, and finally when they're done, they will package the container and build it. And from that on, you have this packaged container, an image, and this image can be at risk. And the next one is the registry risk. The container is stored somewhere and it can be at risk at that point as well. It can be an internal registry on premises, or it can be a registry provided by your cloud provider. Next, your containers need to be managed. So some form of an orchestrator will do that for you. And well, the best known one is of course Kubernetes. And all the other flavors like OpenShift. But also here there's a security risk possible. I don't say it will be, but it's possible. And of course, all your containers run as a process on a host, on an operating system, and on that part, that service, there can be also a lot of risks. So you have, when you look at the different stages of containers and where they are and how you promote them to production and deploy them and build them and everything, these risks are identified in certain areas. And the one I talked about earlier already is the image risk. And in image risk, you build all your software for your application, but it can also have vulnerabilities if you miss updates, if your lifecycle management of your container isn't appropriate enough, then you can miss security updates and have vulnerabilities in your software. And also other defects in your configuration can stay in there. Sorry. And you can also, when a developer builds a container, it can take some unknown malware and package it within your container. And last, you have your external repositories, where also your registry comes along, and you can store them as untrusted images. So have no kind of encryption or whatever, no trust between your local network and your external repository where you get your image from. No, the next one is registry risk. So you store your developed and your built containers, and the same here. You can have out-of-date versions, insufficient authentications, sensitive data, mixed data between different corporate workloads like financial and maybe human resources, but also registry attacks by vulnerabilities in images, and these are called KillChain attacks. And if you look at such a registry KillChain or a common KillChain attack, this is an attack from a mechanism created by hackers, and they use kind of malware to attack your container. And with this registry KillChain, there are certain kinds of steps which are typical for a KillChain attack. When you look at, for instance, you pull your generic image from Docker or GitHub, it can already be infected. It just happened once with a specific crypto mining malware. And this is an example of how it worked. You have your Docker images, which you pulled from your Docker or GitHub, already told you. And then with the pull, you get the malicious software in-house. And from that on, you also create the backdoor for your for the hackers to infiltrate. And this infiltration goes with certain steps. First of all, the lateral movement. So look into to the images, or look into the internal network where they are, and look for weaknesses, discover weaknesses using all kinds of tools. And what was happening in here, they misused the containers with the infected malware to use it as a crypto mining tool. So all the containers were infected with this tool. So you can see that without knowing, you pull in these infected images and run all kinds of malicious software in it. Another important risk is the orchestrator risk. The orchestrator, which might be Kubernetes, which is the most common, most used orchestrator amongst container native landscape. But it can have a certain kind of risks within. Like in accessibility terms, you can have administrative access which you don't need, which is not being identified. So it can mean that from an historical point of view, many orchestrators were designed with the assumption that all users were interacting with them, and they all would be administrators, but this is not the case, of course. In fact, in many cases, a single orchestrator may run different apps, and all these apps can be managed by different teams. So you don't want to have all these teams to become an administrator. Well, another one is maybe unauthorized access, like orchestrators. They often include their own authentication directory service, and this can be separate from the corporate directories which are used within an organization, and that can lead to a weaker account management because there is no monitoring and there's no policy within it to apply the corporate identity management into the orchestrator one. So they become unmanaged or rigorously managed, which is not good, of course, and which can impose a lot of security risks. Already told about mixing workloads of sensitivity, so it can be that you have certain kind of workloads in your container registry, which can, or in your orchestration tool running, which are all from a different sensitivity level. A lot of applications within banks, for instance, or a government have different levels of privacy within the Netherlands, for instance. I don't know how it's at other countries, but within the Netherlands we have different levels of privacy and integrity, and this classification is tells how much an application should be secured. And if you mix those, then it can interact with each other and can conflict with each other, of course. Another one is if you don't implement your orchestrator software at the proper way, then you can also have unauthorized hosts joining your cluster and have weak or same key pairs which are shared across all the nodes. So you have to create your good level of encryption and authentication for every node separately, and also have your communication, your network, your communications of applications, have it encrypted. And looking in containers itself, you have also container runtimes, which expose many configurable options to administrators, for instance. If you don't set them properly, it can lower your security of the entire system. Like an example, if you have a Linux container host, the set of allowed system calls is often limited by default. I mean, you can increase that, of course, depending on what your software is needed for your software. But those are required to have safe operations of your containers, and it can expose at your host operating system as an increased risk from a compromised container. And if you have a container running in privileged mode, it has access to all the devices on your host, which allows it to essentially act as a part of the host and impact all the other containers running on it. And yet another example of an insecure runtime configuration of your container is allowing the container to mount sensitive directories on your host. And in fact, if you look at it, containers should actually make no or rarely make changes to the host operating system file system. And kinds of types of boot or etc, it never should be used by containers. One of the major security risks is at the operating system level. Every operating system has an attack surface, and this is a collection of all ways attackers can attempt to access and exploit your operating system vulnerabilities. Like an example, you have a network accessibility service which provides a potential entry point for attackers, like a port range, a default port range, for instance, which they scan. They can add it to the attack surface, and the larger the attack surface is, the better the odds are that an attacker can find any vulnerability and access it. And this might lead to a compromise of your host operating system, including all the containers running on top of it. Now, the shared kernel, for instance, is also a security risks, and it also has an attack surface, but a little bit smaller than the host operating system, because they don't have any libraries, package managers, and everything for general purpose to run directly a database or a web server app. But sharing this kernel feature, that is really a security risk. And you might say that the level of isolation of container runtimes is not that high as provided by hypervisors. Now, other things like improper user access rights and host operating file system tampering, these also are addressed to hardening your operating system. Like if you have your operating system files tampering, it can be done by insecure container configurations. They can expose their host volumes to a great risk of file tampering. For example, if you have a container which is allowed to mount some sensitive directives on your host operating system, the container can change the files in those directives and set permission bits to others which you don't want. So always be careful to not to mount these sensitive directives by containers. Now, of course, there's not one solution for all these security risks, but if you look at the operating system level, the host level, you can have another way of doing your container runtime running and doing the level of isolation. Now, if you look at this left side diagram, then you can see your typical application container on a host operating system, running as a system process, running in its own namespace, this level of isolation where your app is running, and share the kernel. So the isolation is based on a namespace. Now the solution to have a more isolated container is to use technology which I already mentioned, initiated by Intel, which is called Kata Containers, and now it's called Kata Containers. And Kata Containers, there the kernel is not shared. So in fact, the container runs a bit like a virtual machine, but still also has the characteristics of a container. So you have a small set of application libraries and binaries just meant for your application, nothing more, no overhead. But your kernel is within the container. Looking at some other technology, container stack, I will discuss this later. But for every solution, you can run something more secure. I will elaborate this later in my session. Now, Kata Containers is an open source project at the moment, and it's compatible, in fact, with every current container engine, technology, orchestration engine, everything. So you can use it with Docker engine. It's compatible with all your Docker software and images and Docker files. And it also is compatible with Kubernetes because it's based on the Open Container Initiative. It used the container runtime interface. Recently, Docker wasn't more the de facto standard to be used on Kubernetes, and more like these initiatives like Cri-o and Containerd are more the common ways of running your containers and running your container software. To look at the compatibility of container runtimes and the virtual machine containers like Kata is, you can see here a diagram of how Kata containers use these runtimes. So if you have the traditional OCI runtime runC, which relies on kernel features such as container groups, C groups, and namespaces to provide the isolation when you spawn the containers, there you can see that the result of they are sharing the same kernel, and already told this is less secure than using other types of traditional virtualization using a hypervisor. So when you look at Kata container and Docker and other compatibility there, you can see it uses another version of shim, and shim is a input and output manager for your containers. And within the container, and the pod level of isolation is based on hypervisors. So as I told before, Kata containers use an extra virtualization in the form of a hypervisor. When you look at the hypervisors which are available currently, you have the type 1 hypervisors, which are Xen, Hyper-V, VMware, and they are called type 1 because the guest operating system where the hypervisor runs, the host operating system where the hypervisor runs, doesn't have to be aware of the guest operating system. It's the extra layer in between, which provides everything for the guest operating system to be isolated and run its own thing without knowing anything about the outside world. Now for the Kata containers, the hypervisor which is running is KVM, and KVM is actually also a type 1, but in this case it's used in combination with an emulation which is called QEMU. And QEMU dynamically translates all the system calls of your guest operating system on your container into system calls for your host operating system. So it can take advantage of all the hardware acceleration which are offered by KVM. And for the emulation of Kata containers, you can use the default implementation of QEMU, but you can also use Firecracker. Firecracker is running on Amazon, and it's a bit similar to QEMU, but there are some small differences. There's a faster startup time and low memory overhead, and they are called micro VMs running, and it enables you to pack thousands of micro VMs on the same machine. So every function, container, or container group can be encapsulated within a virtual machine barrier. So you have a lot of workloads running in the same level of virtualization. You must have heard my dog barking in my previous slide. Maybe I was saying something wrong, I don't know. He disagreed with it. Anyway, well, to run your Kata containers using this virtualization and emulation level, you have to enable it on CPU level and enable some flags in your CPU to run this certain kind of emulation. And this needs to be done within the BIOS. And this is a typical overview of how the internals of a Kata container virtual machine is built up. So on the right side you can see the Kata virtual machine / container. Within the container there is a separate kernel, and it's also isolated within the container namespace. So even within the container you have some isolation. And then in between there is a Kata agent which talks to the hypervisor. And outside the container you have the standard gRPC to communicate with the Kubernetes cluster through shim for input and output, and for the runtime specifics for your commands and all the pod commands and runtime stuff. Well, and because it's open source Kata and also Cri-o runtime, it is supported for any cloud infrastructure, usually unmanaged cloud infrastructure. So you can run it on Azure Kubernetes service or any other. Well, you can implement it by yourself, but default all these managed Kubernetes service comes with Docker runtime. So you can build it up with your own virtual machines, build your own Kubernetes clusters using other runtimes like Containerd or Cri-o and Kata containers. And additional tool sets, already mentioned it. to be more and more secure also in how to build and operate your container images, you can use additional toolsets like Podman and Builder and Scopio. Well, here I show you some integration, how you integrate your Kata into your Docker runtime, for instance. Can be also another one, but in this case I chose for Docker. Docker, you have to tell the daemon to have the native group driver set to systemd, because it needs to be managed by your system calls. And you can also say to your Docker startup that you will run the Kata runtime instead of the Docker runtime. So there's a little bit of change in your configuration and no change in your Docker files of any, because you can use them all as the same as you already did. So no changes in that. And of course we look at the Kubernetes integration itself. So looking at Kubernetes, this is a default Kubernetes cluster. It's not high available, but usually have multiple masters, of course. But here you can also see all the security risks I already mentioned before. So access to all the nodes, have improper nodes added to the cluster, for instance, but also access to the nodes, to the attack servers, which I already mentioned before. Next one, also for the worker nodes, of course. The control plane, so the Kubernetes management API, where you have your API server, your scheduler, controller, and everything running, which can impose a security issue. All the daemons running, your kubelet daemons, your kube proxy, your container runtime, either it's Docker or any other. If it's not isolated using some kind of hypervisor, then it still can still be compromised. And also, of course, on all the worker nodes, access to the kubelet or intercept or your inject application traffic with, well, all kinds of technologies hackers or intruders use, like SQL injection or other ways of getting data out of it. And of course, we want to integrate Kata containers into our Kubernetes cluster. So first things you need to do is to install the necessary packages for running your runtimes for Kata container, Cri-o or Containerd. And you have to instruct your kubelets to use the proper container runtime, because otherwise it will use the default Docker runtime. Build your Kubernetes master or change your Kubernetes master to use the proper runtimes. In fact, you don't need to rebuild your cluster. You can drain the nodes and update them with the new configurations. And you can even say, well, if I'm on a stage of testing, I want to use certain nodes using the Docker runtime and other nodes using another runtime, then you can use multiple runtimes and every node can run its own container runtime. So that's pretty cool. And this is an example of how you do this. So, well, on one of the work nodes, we want to use Cri-o runtime, for instance, instead of Docker. So configure the kubelet daemon with the proper configuration for Cri-o. And then you have to re-initiate your nodes to the cluster using the right Cri-o socket. And in this case, it's going to be Containerd, but it can also be Cri-o. Depends on what your configuration. And here this results then in 3 nodes running, 1 master, 2 worker nodes. It's not the most best configuration, but it's more like to show you where you can see at the most right part that all nodes have their own container runtime. 2 are running on Cri-o and 1 is running on Containerd. So that's really pretty a cool thing if you want to test it and not certain if you want to step over and migrate to a new runtime. Also, another thing you need to do is to say to your Kubernetes cluster to make use of this QEMU hypervisor. This can be done by using a Kata or by using a Kubernetes runtime class. For this purpose, it will be a Kata runtime class. And in case of where you run multiple container runtimes and multiple container configurations, like using the de facto shared kernel container or the virtual machine container, you can label, of course, an obvious technology within Kubernetes. You can label your nodes, one to run Kata containers and other not to run Kata containers. So that those are options to do, or maybe you can change your nodes or do any other kind of labeling to say which nodes should run the proper configuration. And then you can instruct your deployment and your pods to run the Kata runtime class. And then when you start up your container, then you can see it's running with the QEMU virtualization software. So this is an example of how to label your nodes for a Kata runtime class. And in this case, I only labeled one node to run the Kata runtime. And next, if you have a application deployment, this is a simple one using a PHP application. Here you have to implement the Kata runtime class, where you say to the deployment and the running pods behind that to use the Kata QEMU runtime class. And if you then deployed your application, rolled out your deployment, you could go to one of the nodes, which is labeled to run as a Kata runtime node. If you then do a grep on QEMU, then you can see the QEMU software is called by the container which is using this software. So there you have your proof of the container is running Kata containers using hypervisor, using QEMU, and using this higher level of isolation to protect all your sensitive data. There are some additional tools as well, which I like to mention at the end of my presentation. You have some additional tools like Podman and some other tools, which can be used to run your build and deploy more secure. Like you have Podman. Podman is a tool which can replace your Docker command line interface. So like Docker, you have to start as a daemon service, and for Podman you don't have to do this. It's daemonless. It doesn't use any client server model. So a container is a child process, and it inherits the same UID. So you always know, you can track every kind of record. And it can be run as a non-root user, which is a major improvement for building up your containers and also pushing it. Another additional tool is Builder, which is quite similar to Podman. The Builder is specifically meant to build OCI-based container images. They also can run rootless, and same as Podman, they can be used without any runtime daemon. So that's also a really cool feature. So the combination of all these tools can make it very much more secure, and like a Builder has a better secret handling, for instance, for subscriptions, and credentials to secure registries. Well, it's also the size of the created image is much smaller, so your attack surface will be also a lot smaller. All the software which is being used by create a container will be not contained in the image, which is good because you don't want to have an overload of unnecessary software into your to your container. And last but not least, you can still use a Docker file to build the container, so it's backwards compatible, in fact. So you don't need to do a lot of things to use these tools to have better security. And this will secure your entire landscape in the most broad way of understanding. Okay, that completes my session. I hope you enjoyed it. I hope you enjoyed the rest of your days within KubeCon and Cloud Native Con and all the other conferences which are all running besides of it. If you have any questions, well, here are all my socials, but I also think the organization will provide you some way of asking questions around this topic. So have a good day, have a good conference, and see you maybe somewhere in real person. Bye bye.